Mobile Edge Computing (MEC). I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering, Indian Institute of Technology, Patna. Contents. So, contents of this lecture: introduction to mobile edge computing, then MEC architecture, then task offloading in MEC, then resource allocation in MEC, then mobility management and resource migration in MEC. So, here we are going to understand the earlier MEC, which is called a mobile edge computing. Now, it is called multi-axis edge computing, and it is a part of now, that is, the edge computing has become a part of 5G, that is the cellular network. We will see all that aspects, what is that architecture of MEC in 5G, and is there any standardization or not. Then what is the meaning of task offloading in MEC, how the MEC is going to help in task offloading. Then if the task is offloaded to MEC, then how the resource allocation is being carried out in MEC, and mobility management and resource migration in MEC. So, mobile edge computing. So, now you can understand that advancements in the wireless networks, that is the number of mobile phone users, have increased dramatically, and moreover these phone usage is not limited to the voice call, but many other type of services and application, now apps are now being used here. For example, it is a shopping, or it is calling app based cab, and so on. Now, for very high bandwidth and low latency service, therefore, there is a requirement of an edge computing in this particular scenario of this particular access. So, in the access technology. So, in the edge computing, the intermediate devices between the end users and the cloud, they participate in processing and storage of data as well as execution of the program. So, therefore, mobile edge computing provides IT and cloud computing capabilities with resource access network, that is RAN, in close proximity to the mobile subscriber. So, here you can see that this particular mobile edge computing, that is mobile edge computing, is shown over here. Okay, so, this mobile edge computing will provide the IT and cloud computing capabilities now with radio access in close proximity to the mobile subscriber. So, you can see that this is the mobile subscriber, in close proximity it is going to provide the edge, that is mobile edge cloud, and that is nothing but providing IT and a cloud computing capabilities with the help of with this radio access network, and it is in close proximity. You can see that it is in close proximity to the mobile subscribers. Now, this mobile edge computing provides high bandwidth and a low latency service. So, you can understand that these resources in the form of IT and the cloud is being served very close by you in the radio access network. Therefore, the latency is very low, and also it provides the high bandwidth. Now, therefore, operator can open their radio access network edge to the authorized third party, and MEC can be implemented in the cellular base station. Here you can see that this cellular base station has an MEC within it. So, MEC servers provide the computing resources. Here you can see that the computing resources are being provided by this MEC server, storage capacity, connectivity, access to the user traffic, and radio and network. So, this why is beneficial compared to the cloud based capabilities of providing same computing resources, storage, but it comes from a very far distances, adding to the very high latency into the services and also provides very low bandwidth, because most of the bandwidth is being utilized for long haul network to serve the computing. So, therefore, the characteristics of such mobile edge computing are that it is often provided in the form of on premise, and it is very close proximity based services to the subscriber. It offers a low latency, and it also gives a very important notion of location awareness and also retain the network context. So, you can see these are several advantages. So, the applications requiring the low latency, location awareness and network context, they have to now depend upon the edge computing, and the edge computing when meets to the mobile network, it becomes MEC. Now, there are several models and there is no standard way of doing it. Standardization is yet to evolve. So, there are various models for mobile edge computing. The first one is called MCC, that is mobile cloud computing, before or a precursor to the MEC. That means, before MEC it was called mobile cloud computing, then came the fog computing and then cloudlet, and now the very recent thing which is called. So, in the mobile cloud computing, maybe in the next slide we can see. So, mobile cloud computing MCC is a paradigm where the computations and storage takes place inside the cloud instead of the mobile device. See in this particular example. This is the typical example of mobile cloud computing. So, here you can see that these particular requirement of the resources required for the end user will be served long haul from the cloud. So, it is called mobile cloud computing. So, that means, this cloud computing which is going to be meeting the requirements of the mobile users from the cloud, called mobile cloud computing. So, mobile cloud computing is a paradigm where the computations and the storage takes place inside the cloud instead of the mobile devices that we have seen in the previous figure. So, the users access the data from the cloud whenever it is required. Similarly, a computation has to be executed that is performed inside the cloud, and the users will be interested to get the results. So, in mobile cloud computing, a user equipment may exploit computing and storage resources of a powerful distant centralized cloud. So, here you can see that it is a distant centralized cloud, and here you are having the mobile phone users, and now this particular user equipment UE will exploit the computing and the storage of the cloud, centralized cloud. This is called centralized cloud, and which are accessible through the network which is called a core network. CN short, core network of a mobile operator and the internet. So, this MCC, that is mobile cloud computing, brings into several advantages. First is that now it will extend the battery lifetime by offloading the energy consuming computation to the cloud. it will save the energy. Which is often the battery powered, enable the sophisticated applications to the mobile users. Now, mobile users is no longer constrained with the computing and storage of the mobile handsets, but rather it can leverage or it can use a rich set of computing and storage available by the cloud. So, therefore, some difference between the mobile cloud computing and mobile edge computing. First of all, that mobile cloud computing is fully centralized approach with a forms of computers usually placed at one or a few locations, whereas edge computing is supposed to be deployed in a fully distributed manner. Now, then comes the next aspect, which is called a fog computing. So, fog computing was introduced in 2012 by Cisco to enable the processing of applications of billions of connected devices at the edge of the network. So, fog is one of the important enabler for Internet of Things, IoT, and the big data applications. Now, the next part is called cloudlets. Cloudlets is a computer or a cluster of computer that offers the cloud services to the users by acting as an agent. So, the cloudlets contains cache copies of the data stored inside the cloud. So, when the user requests to access to the data, the cloudlet meets the requirements. So, as a result, the latency is reduced in this particular manner and the quality of service gets enhanced. The cloudlet is mainly popular with the wireless access environment. The fact that cloudlets are supposed to be mostly accessed by mobile users through Wi-Fi connection is seen as disadvantage, since the UE, that is user equipments, have to switch between the mobile network and the Wi-Fi whenever the cloudlet services are exploited. Therefore, this particular benefit, to get this cloudlet related benefits of the proximity of computing and storage, is done through switching from the mobile network and Wi-Fi network. So, that means these kind of proximity or latency reduction in the cloudlet is splitted between, or you have to switch between the mobile network and the Wi-Fi. Why? Because this cloudlet does not provide the integration of computing and storage within the mobile network. So, therefore, comes with this particular advantage called multi-access edge computing. So, earlier it was a mobile edge computing. Now, that mobile edge computing is now changed to multi-access. Why? Because there may be multiple access technologies to provide this edge computing. Therefore, it is called multi-access edge computing. So, from mobile users point of view, the most notable drawback of previously mentioned edge computing paradigm is that quality of service and quality of experience for the users can be hardly guaranteed, since the computing is not integrated into the architecture of the mobile network that we have already told in the example of a cloudlet. For example, in the cloudlets. Therefore, 2014, the industry specification group within European Telecommunication Standard Institute (ETSI), they outlined the concept of a mobile edge computing, which integrates the edge computing into the mobile network architecture. So, let us see about the multi-access edge computing architecture. Multi-access edge computing architecture. So, now you can see that several multi-access edge computing concepts are built upon the purpose to smoothly integrate the cloud capabilities into the mobile network. So, there may be many different ways to integrate this, and so we will discuss some of them, and we call it as an architecture of an MEC. So, let us see some of them. The first one we are going to cover is called small cell cloud, then mobile micro cloud MMC, then fast moving personal cloud FMPC, then follow me cloud, that FMC, then consult and etc MEC finally. Let us see about the small cell cloud. This is the way, this is an architecture of MEC. This is one such architecture of an MEC called small cell cloud, was introduced in 2012 by European project called TROPIC, is to enhance small cells, that is SCENBs, to enhance these SCENBs like microcell, picocell, femtocell by additional computation and storage capabilities. So, you can see that here this is an additional computing and storage provided at SCENBs to enhance a small cell, that is called SCENBs. Now, this is one aspect, that is these computing, additional computing is to be provided. You can see that here in this SCENB also the additional computing is being provided, that is enhanced small cell called SCENBs, enhanced small cells. Okay, then the cloud enabled SCENBs provide the edge computing as well. Here you can see that this is the cloud enabled SCENB provide the edge computing. So, the cloud enhanced SCENB can pool their computation power exploiting the network function virtualization, and the computing resources are often virtualized here. By means of virtual machines located at this SCENBs. So, here it is the virtual machines. Now, because a high number of SCENBs is supposed to be deployed in the future mobile network, the SCECs can provide enough computing power for the users, especially for the services and applications having stringent requirement on latency. In order to fully and smoothly integrate SCC, that is small cell cloud concept into the mobile network architecture, a new entity denoted as small cell manager SCM is introduced to control the SCC. So, here you can see that this is small cell manager, SCM is called small cell manager is introduced over here. Again I am repeating. In order to fully and smoothly integrate SCC concept into the mobile network, a new entity that is called small cell manager is introduced to control the SCC, control the SCC. Now, this small cell manager SCM is in charge of the management of computing and storage, resources provided by SCENBs. Since SCENBs can be switched on or off at any time, the SCM performs dynamic and elastic management of the computation resources within SCC. So, the SCM is aware of the overall cluster context, both radio and the cloud wise, and decides where to deploy a new computation or when to migrate an ongoing computation to optimize the service delivery for the end users. Now, here you can see in the figure A, the SCM may be deployed in a centralized manner called centralized SCM, either as a standalone SCM located within the RAM, within the RAN, that is radio access network, close to the cluster of SCENBs, or an extension to MMEs like this one in the core network, that is SCM in the core network. Now, further if you see in the figure B, a distributed hierarchical SCM, it is not centralized, but it is a distributed. So, the SCM can be deployed in a distributed hierarchical manner, where the local SCM, this is called local SCM, LSCM, local SCM, or a virtual local SCM, it is a virtual local SCM, manages the computing and storage resources of SCENB's cluster in the vicinity, while a remote SCM, that RSCM, this one, located in the core network, that is in the CN, has the resources of all the SCENBs connected to the core network at its disposal. Now, coming to the next type of architecture for MEC. Is called mobile micro cloud, MMC, mobile micro cloud. So, like SCC, small cell cloud, the mobile micro clouds or MMC allows the users to have instantaneous access to the cloud services with a low latency. With SCC, the computation and storage resources are provided by interworking cluster of SCENBs. The UE exploit the computation resources of a single MMC. So, here you can see that all the UEs will exploit the computing resources or storage of single MMC, that is, which is typically connected directly to the wireless base station that you can see here in the picture. Unlike SCC, the MMC, that is mobile micro cloud concept, does not introduce any control entity into the network, and control is assumed to be fully distributed in a similar way as VLSCM solution for SCC. So, the MMC are interconnected directly or through the long haul or through backhaul in order to guarantee the service continuity if UEs move within the network to enable the smooth virtual machine migration among MMC. Now, the next type of architecture for MEC is fast moving personal cloud, MOBI SCUD. Integrates the cloud services into the mobile network by means of software defined network and NFV, that is network function virtualization, while maintaining the backward compatibility with the existing mobile network. So, when compared to SCC and MMC concepts, the cloud resources in MOBI SCUD are not located directly to the access nodes such as SCENBs or ENB, but at the operator's cloud location. This is the operator's cloud. within the RAN or close to the RAN. So, these clouds are assumed to be highly distributed. Similarly, as in the case of SCC and MMC enabling the cloud to all UEs in the vicinity. MobiSCUD introduces new control entity called MobiSCUD control MC. Here this is called MobiSCUD control, that is called MC. MobiSCUD control called MC. So, which interfaces with the mobile network, SDN switch and the cloud of operator. Basically, MC has two functionalities. First is monitoring control plane signaling like this one. So, message exchange between the mobile network element to be aware about user activities. The second part is called orchestrating and routing data traffic within SDN enabled transport network to facilitate the application offloading and virtual machine migration if the user equipment moves throughout the network. The next architecture for multi-access edge computing is called Follow Me Cloud, FMC. So, the key idea of Follow Me Cloud is that the cloud service is running at the distributed data center. DCs follows the user equipments as they roam throughout the network. So, you can see this is the user equipment, they get the computing and the storage from a distributed cloud. So, when compared to the previous MEC's concepts, the computing and storage power is moved farther from the UE in the core network of the operator. Nevertheless, while previous MEC's concepts assume rather centralized core network deployment, the FMC leverages from the fact that mobile operator need to be decentralize their network to cope with the growing number of UEs. So, 3 centralized core network used in the current network deployment is assumed to be replaced by the distributed one. For the convenience of mobile operators, the data centers may be located at the same place as distributed serving gateways or the packet gateways. So, FMCC may be deployed either centrally or hierarchically with global FMCC and local FMCC. So, here this particular FMC introduces new entities into the network architecture called DC GW. So, here you can see DC GW mapping. So, DC GW mapping entity maps the data center to the distributed serving or a packet gateways according to the various metrics such as location or a hop count between data center and the distributed core network in a static or a dynamic manner. That is what is shown over here, this mapping to this SGW, that is the serving gateway and the packet gateway. This particular mapping is done based on the various parameters. The next architecture for MEC is called CONCERT. CONCERT is the short for Concept Converging Cloud and Cellular Systems. So, CONCERT assumes to exploit NFV principles and SDM technologies like above mentioned solutions. The computing and storage services utilizes both the conventional mobile communication and cloud computing services are present as the virtual resources. The control plane consists of a conductor, which is the control entity managing communications, computing and storage resources of a CONCERT architecture. The conductor may be deployed centrally or in a hierarchical manner for better scalability. The data plane consists of the radio interface equipments physically representing the ENB and SDN switches and computing resources. The computing resources are used both for baseband processing similarly to CRAN and for handling and application level processing. So, CONSORT proposes hierarchically placement of the resources within the network to flexibly and elastically manage the network and the cloud services. Local servers with low computation power are assumed to be located directly at the physical base station, and if the local resources are not sufficient, regional or even the central servers are exploited, which is shown here in this particular figure. Now, the next particular architecture of MEC is proposed by ETSI, is currently involved in the standardization activities in order to integrate MEC into the mobile network. So, MEC can be exploited either by UE application located directly in the UE or by third party customers via the customer facing service CFS. Both the UE and CFS portal interact with MEC system through a MEC system level management. So, the MEC system level management includes a user application lifecycle LCM, proxy which mediate the request such as initiation, termination, relocation of user equipments, so UE's applications within MEC. System to the operation system support OSS. Of the mobile operator. So, the OSS decides if the requests are granted or not. The granted requests are forwarded to the mobile edge orchestrator. Here you can see. So, mobile edge orchestrator is the core functionalities of MEC system level management, as it maintains overall view on the available computing, storage, network resources and MEC service. The mobile edge orchestrator allocates virtualized MEC resources to the applications that are about to be initiated depending upon the application requirement, that is the latency. The orchestrator also flexibly scales up downs the available resources to the already running applications. MEC system level management is interconnected with MEC server level management, constituting a mobile edge platform and a virtualized platform. So, MEC system level management manages the life cycle of the applications, application rules and service authorization, traffic rules, etc. So, MEC server level management is responsible for the allocation, management, release of the virtualized computation storage resources provided by virtualization infrastructure. So, MEC server represents the virtualized resources and the hosts the MEC application running on the virtual machines on the top of virtualization infrastructure. So, MEC architecture, if you make a comparison, so the MEC concept where the control entity of an MEC concept, that is SCC, is called SCM. In MMC there is no control entity, and in MobiSCAT it is MC, and FMC it is called FMCC, and in CONSORT it is called conductor. At CMEC it is called mobile edge orchestrator. So, in all the cases you can see most of the cases it has a control entity. Then there is a concept of a control manager in all the MEC architecture. So, for SCC this control manner is centralized, decentralized, hierarchical, both are there depending upon, where in MMC it is decentralized Mobius card it is decentralized, FMC it is centralized and decentralized. Option with the hierarchical FMC and decentralized option without FMC controller. Concert it is centralized and decentralized and hierarchical. MEC at CMEC it is centralized. So, control placement now in SEC in RAN, that is at ENBs, enhanced E node B, or in the core network. MMC it is called, it is placed at MMC ENB. Mobius card it is between RAN and CN, and FMC it is co-located with existing nodes or run software on DC, and concert it is not applicable. Computation and storage placement, SCC it is SCENBs, that is the cluster of SCENBs, and MMC it is ENB, and Mobius card it is the distributed cloud within the RAN. FMC it is that data center which is close or co-locating with the distributed core network. Then concert is with ENB, regional and central servers that we have seen in the previous slides. So, at MEC computation and storage placement is at ENB aggregation point and edge of the core network. So, MEC deployment options, that MEC server directly at the base station. So, MEC services will be provided by MEC servers, which have the computation storage resources disposal. There are several options where the MEC servers can be deployed. The first option is to deploy MEC server directly at the base station, similarly as in the case of SCC or MCC. The second option, that is MEC servers at the cell aggregation sites or at multi-RAT aggregation. The second option is to place the MEC servers at cell aggregation sites or at multi-RAT aggregation point that can be placed, that can be located either with an enterprise scenario or a public coverage scenario. The third option is to move the MEC servers farther from the UE and locate it at the edge of core network. Then selection of MEC servers deployment depends on many factors such as scalability, physical deployment constraints, and a performance criteria, for example delay, etc. Now, deploying the mobile edge computing, that is the edge computing in outdoor scenarios will improve the mobile users quality of experience, improve the infrastructure's efficiency, tight integration with the radio equipment. Edge computing in the indoor scenario will improve the machine to machine scenarios, retail solutions, stadiums, airport, big data analytics. Now, let us see one of the most important critical use case regarding the MEC is the computation offloading. This is the use case of MEC, that is called computation offloading. A critical use case regarding MEC is the computation offloading, and this can save the energy or speed up the process of execution of computation. So, a crucial part regarding computation offloading is to decide whether to offload or not. In the former case, also the question is how much and what should be offloaded. So, the decision on computation offloading may result into the local execution. The whole computation is done locally at the user equipment, and the offloading to the MEC is not performed. Fully offloading, the whole computation is offloaded and processed by MEC. Partial offloading, a part of the computation is processed locally while the rest is offloaded to the MEC. So, task offloading So, computation offloading, that is the partial offloading, is a very complex process affected by various factors such as user preferences, radio and backhaul connection quality, user equipment capabilities or cloud capabilities, resource availability and so on. An important aspect in the computation offloading is also an application or a type, since it determines whether full or partial offload is applicable and what could be offloaded. So, task offloading objectives formally and mathematically define the goals and guides the offloading solution. This is very important. So, objectives of the task offloading can be categorized as based on energy. So, the total energy consumed by offloading is consumed energy to send the task from the device to the server, the consumed energy to execute the task at the edge server, and consumed energy to return the task called total energy. Latency is the total time of transferring the task to the edge server, time taken execution in the servers, and the time to return back the results. Then response time is the interval between the offloading the task from local device to the remote servers, receiving the suitable answers in the device. The cost is the cost of the edge and the cloud resource usages, and sometimes is the penalty cost due to the SLA violations. There are many two kinds of resources: private resources, public resources used for finishing offloaded task for the service provider. QoE, that is quality of experience and quality of service, measures user satisfaction, combination of various factors such as latency, response time, power saving, bandwidth and resource requirements. Factors affecting the task offloading influence the decision making process in the task offloading in the edge computing. Selecting the appropriate offloading strategy is dependent upon the latency, that is the local processing for low latency demands, computational resources, availability of resources, power constraints, that is energy consumption and efficiency, data variety, that is large data set or a small data set, task variety, that is compute intensive, and application, that is strict requirement, and mobility, that is the device. So, task offloading in MEC. So, computation offloading or a task offloading is a complex process and can be affected by the number of factors. In particular, this process involves task partitioning, offloading, decision making and distributed execution. So, here you can see that the user application now undergoes to a task partitioning, and then offloading decision making is to be done, whether to offload to the edge or the cloud or not to offload and execute locally. So, task offloading in MEC, the computation offloading decision itself is done at the user equipment here by means of computation offloading policy module. This module decides during each time slot whether the application waiting in a buffer should be processed locally or at MEC with minimizing the execution delay. So, here if it is decided to be offloaded to a MEC server, then the transmission unit will take place. If it is to be processed locally, then it is not sent. So, the decision making means how to utilize and manage the offloading process in the practice. The user equipment need to be composed of the following component: code profiler, system profiler and decision engine. Application model, what and how could be offloaded depends upon the application running on the user equipment. So, offloadability of an application enables the code or data partitioning and parallelization in two types: fully offloadable and partial offloadable. So, here you can see this, the user application is local and local execution is possible, and non-offloadable and offloadable. So, offloaded applications are executed at the remote servers. Now, the knowledge on the amount of data to be processed. So, the applications can be classified according to the knowledge on the amount of data to be processed, fixed input, that is the amount of data to be known beforehand, interactive input, that is continuous execution application, and there is no way to predict how long they will be running. Now, task offloading, that is the application model, dependency on the offloadable parts, independent and dependent, and the dependency relation between the individual component can be expressed by the component dependency graph, that is CDG, or a call graph. So, here in this example you can see that the whole application is divided into m non offloadable part 1, 4, 6 and n offloadable part, that is 2, 3, 5. In case 2 and 3 can be offloaded only after the execution of 1, while 5 can be offloaded after the execution of 3 and 4. So, that is what is shown over here. So, you can see that 1, 4 and 6, they are not offloadable part. Now, this and n offloadable parts are 2, 3 and 5, they are offloadable parts. In case 2 and 3, you can see that 2 and 3 can be offloaded only after the execution 1, while 5 can be offloaded after the execution of 3 and 4. So, you can see that is shown in the component dependency graph. This is called CDG. Now, the task offloading in a collaborative cloud edge computing. So, the design of a collaborative cloud edge computing architecture consists of the hierarchical tiers and end devices, network, nodes, central office, remote data center. So, the end devices here can locally process the fraction of the input workloads, horizontally offload to the neighboring, this is the horizontal offloading to the neighboring devices, and vertically offload, this is the vertical offloading for the remaining workloads. So, vertical offloading refers to the transferring the task from higher level processing unit to the lower level ones, for example, from edge server to the cloud. So, this is the edge server, from edge server it may offload to the cloud server, it is called vertical offloading. Pros means advantage that cloud has more computing power compared to the edge. Cons is that it will increase the latency due to the data transmission delay. Horizontal offloading refers to the distribution of the task across the multiple processing units, for example, distributing the single server load across multiple servers. So, task offloading, in summary, the task offloading process starts at the end devices and leverages the benefits of the added computational resources, allowing to increase the quality of service and quality of experience while extending the battery lifetime of the end devices. Offloading parts of an application from end device to the remote edge or a cloud arises the number of challenges. Main objective is to minimize the execution delay, minimize the energy consumption at the UE, to find the proper trade off between both the energy consumption and the execution delay. So, let us see that task offloading with the objective of minimizing the execution delay, how that is all done. So, one of the advantages introduced by task offloading is the possibility to reduce the execution delay, that is D. So, in case of UE performs all the execution by itself, no offloading, the execution delay, that is DI, represents solely the time spent by the local execution. In case of offloading is performed, the execution delay by offloading incorporates 3 different parts: transmission duration of the offloaded OT, computation or processing time at the server, and the reception, the duration of the processing. So, DO is having 3 components. In case it will be favorable for user equipment to offload its task to the remote server whenever delay is less than doing at internal, that is in an internal delay is more than. So, it will offload here in this case. You can see that this will offload to the remote servers. So, here user equipment performs all the locally, since the local execution delay is significantly lower than expected. Here you can see that d I is less than to offload to the remote server, as the local execution is notably higher compared to the local to the this one. So, it will be that in that case offload it. So, minimizing the execution delay, again it is quite similar to that. So, here if it is, so the offloading decision is defined by this inequality d O if it is less than d I. So, minimizing the energy consumption while satisfying the execution delay constraints. So, here E O is equal to that means E O T, that is the transmit the offloaded data for the computation, plus E O R receive the result from that. So, if let us say the energy is less in offloading, then it will favorable for U E to offload its task to the remote whenever this particular thing is there. So, here in this particular example, the user equipment 1, this one performs the computation locally, since the energy spent by the local execution E I is significantly lower than the energy required for transmission offloading E O. So, it will perform locally, it will not offload. Contrary, as far as the second user equipment will offload its task, as the energy required by computation offloading is significantly lower. So, wherever it is energy is lower. So, by doing in the remote server, if it is lower, it will do that. Now, minimizing the energy consumption while satisfying the execution delay constraint, that we have already covered. Now, coming to the resource allocation in MEC. Resource allocation in multi-access edge computing refers to the process of distributing computing resources such as CPU, memory, storage among different application services that are running on the edge. So, MEC enables the mobile devices to offload their compute intensive task to the edge server located closer to the edge, which can improve the performance. So, resource allocation can be dynamic and adaptive depending upon the current workload of the edge server, the quality of service requirement of the application, and available network bandwidth. So, the goal is to ensure the resources are utilized optimally. So, resource allocation decision is full or partial offloading of an application of an MEC is accompanied by the proper allocation of the computing resources on the edge nodes, and if required the cloud as well. So, the selection of computation placement is influenced by the ability of the offloaded applications to be parallelized or partitioned. So, if parallelize or partition of the application is not possible, only one physical node may be allocated for computing. In the other hand, the offloaded application may be processed by the resource distributed over several nodes. So, that is shown over here in the form of virtual machines. So, here you can see that this particular user equipment has only one physical node. But why? Because the partitioning is not possible. You can see that there is no partitioning. So, it will be now resource allocation in MEC will be happening in this one virtual machine will be doing this. Now, whereas this user equipment, his particular application is divided into 3 different tasks, 1, 2 and 3. What it will do is that it will transfer its one of the MEC is one of the tasks in this MEC, that is ENB2. One of the tasks it will transfer here that is a resource allocation from this MEC, that is ENB3, and one more partitioning will be assigning the resources of ENB1. So, the main objective of resource allocation problem in MEC is maximization of the amounts of applications served by MEC while satisfying the delay requirement of the offloaded and optionally the energy consumption. So, the decision where the individual application should be placed depending upon the application priorities, application delay and availability of resources. So, resource allocation in MEC. So, in the virtual machine based resources, the resource allocation problem has to deal with the minimization of execution delay of the offloaded application, along with minimizing the communication and computing resources and the virtual machine migration cost. So, the computing nodes are represented by SCENBs, that is what is shown over here, and the virtual machine migration may be initiated due to SCENB shutdown. For example, if let us say there is a shutdown, so it will be a migration. So, the whole problem can be formulated as the VM allocation at SCENB and solved by the means of Markov decision process. Now, clustered resource allocation. Now, forming the cluster of SCENBs is a common approach to optimize the resource allocation in the mobile edge computing. So, clustering involves grouping together a set of SCENBs that are geographically close by. So, you can see here they are being grouped together because they are close by. So, SCENB1, SCENB2, SCENB3 together are being clustered or being grouped together and can be controlled and managed by a single entity as a single entity. Forming clusters can manage the resource allocation among SCENBs and improve the overall performance of the system. So, clustered resource allocation requirement to form the cluster, define the clustering criteria, define the cluster size, assign the provisioning resources, monitor and optimize. Now, selection of the compute nodes. So, selection of computing nodes can significantly influence not only the execution delay, but also the power consumption of these nodes. Following are the key observations which impact on the size of the clusters or on both the execution latency of the offloaded application and the power consumption. So, backhaul topology, then backhaul connection and the number of nodes. Clustering strategies in MEC. So, clustering strategy, there are three different clustering strategies can be followed. In the first strategy, SCENBs are selected in order to minimize the execution delay, since all the SCENBs in the system model are assumed to be one hop away. So, all the SCENBs are included in the computation offloading and resource allocation. This can significantly reduce the execution delay due to the fact that the computation gain is far greater than the transmission delay. The objective of the second clustering strategy is to minimize the overall power consumption of the cluster. In this case, only serving SCENBs is preferred to compute. Thus, any computation at the neighboring SCENB is suppressed to minimize the power consumption of SCENBs. This, however, increases overall latency and high variation of the computation load. The last clustering strategy aims to minimize the power consumption of each SCENBs in the cluster, since the power consumptions in the individual SCENBs is highly imbalanced in the second strategy. Now, cluster allocation in MEC. Cluster allocation refers to the process of assigning clusters of SCENBs to UEs. So, in multi-UE scenario, whenever a UE is about to offload the data to the computation for the computation, the computing cluster is assigned to it. Consequently, each UE has assigned different cluster size depending on the application and the UE's requirements. The main objective in this case is to minimize the power consumption of the clusters while guaranteeing required execution delay for each UE. Some cluster allocation strategies include successive cluster optimization. The main objective of successive cluster optimization is to improve the performance of MEC by dynamically adjusting the cluster size and resource allocation based on changing workloads and QoS requirements of the application. In the successive cluster optimization process, the MEC system can split a cluster into smaller clusters if the cluster is becoming overloaded, or merge smaller clusters into a larger cluster if the clusters are underutilized. This adjustment of cluster size allows the MEC system to allocate resources more efficiently among the clusters. Cluster allocation in MEC. Joint cluster optimization. The core idea is to jointly compute clusters for all active users requests simultaneously, to being able efficiently distribute computation and communication resources among the UEs and to achieve higher QoE. The main objective in this case is to minimize the power consumption of the clusters while guaranteeing required execution delay for each UE. Static clustering. In the static clustering approach, once the clusters are formed, the allocation of the resources among the clusters remain static and does not change based on the changing workloads and QoS requirements of the applications. Usually, the resources are divided equally among all SCENBs. Static clustering has the advantage of simplicity and ease of implementation. However, it may not be suitable for MEC systems with highly dynamic workloads and QoS requirements, as the static allocation of the resources may result in underutilization or overutilization of the resources. Thank you.